Okay, I'm going to go over the 6.1 quick check. So the first question here is talking about a situation where we have some ice put into water. So a large ice cube is added to a glass of room temperature water. So what happens to the temperature of the liquid water? Well, obviously it's going to decrease, because that's why we put ice into water. Now the energy change to the liquid water. So what's going on to the liquid water? If the energy is, if the temperature is going down, then the water is losing some of its energy. So that is endothermic. Okay, so the liquid water is losing energy here. Now, the ice cube is actually the system. So if we want to consider the ice cube that's in here, okay, the energy change of the ice cube then must be exothermic, because that's what's giving off the energy. Okay, I just said that wrong. Okay, it's got to be endothermic, okay, because of the fact that, where is the water losing energy? It's losing water to the ice. Okay, so the ice, as is H2O, that's a solid, okay, is going to pick up some energy and turn into H2O, that's a liquid. Okay, so the energy change of the system is that it is endothermic. And the temperature of the ice cube, okay, the temperature of ice cube actually doesn't change at all, okay, because remember from our heating curve, we know that as something melts or boils, okay, then it stays constant to that process. So it stays at 0 degrees until it's all melted. But the ice cube is changing, okay, it is gaining energy, and it's gaining energy in terms of potential energy. So it's a potential energy change. Now, explain in terms of interparticle forces. In the ice, okay, all these little water molecules are, very close to each other, and they're attracted to each other with the hydrogen bonds, and it's very, 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 a strong bond between those. And then as it turns into a liquid, okay, it's got to gain energy. So when you get to the liquid form, then these guys are a little bit more, spread out and random. Actually, they're closer together, but they're not all stuck together in a crystal. So in the solid, we have a solid crystal turning into the more loose H2O liquid. Second part here, calculating the enthalpy from data. So if we had a 5-gram sample of propane and we're going to burn it, it warms up some water. So this would be done in a calorimeter from 20 to 80. So we can see that our delta T, okay, is going to be 60 degrees. And so what's the delta H of combustion for the propane? Okay, so we want delta H. So first thing we're going to do is figure out our Q. So Q equals MC delta T. Okay, the mass of the water, we have 100 grams of water. Okay, times C up at the top of the page, 4.18 joules per gram degree. And times 60 degrees. And we can calculate that. And I get that to be 25,080 joules. Okay, or I might write that as 25.080 kilojoules. And that's my Q, but I want to say, well, how much would that be as a delta H? So delta H, we know, is the amount of heat divided by the number of moles. So I'm going to put my 25, I'm going to change that to 25.1 kilojoules, and divide by that by the number of moles. Well, I have 0.5 grams of propane, and then I can change that grams into moles. And up at the top of the page here we have that it's 44.09 grams per mole. And the grams drop out, and I'm going to get kilojoules per mole. And I get 2,213 kilojoules per mole. And because, this is burning and it's warming and giving off energy here, then that's going to be a negative value. So what's the sign of the delta H? It's negative. And 2,213, which, significant figures probably round that off to 2,200 kilojoules per mole. So again, I'm using this idea that delta H is my Q, which I can get from Q equals mc delta T divided by N. Okay, second thing here, I have figure out the delta H using delta H of formations. So I'm burning my propane, and I have C3H8 plus 5O2 turns into 3 CO2s and 4 H2Os. And again, because this is standard conditions, which is 25 degrees Celsius, then the water would be a liquid in that case, and that's going to be important. Okay, we know how to do delta H of formations. The delta H of the reaction is the sum of the delta H of formations of the products minus the sum of the delta H of formations of the reactants. So that's going to come out to be 3 times the delta H of formation of CO2, okay, plus 4 times the delta H of formation of H2O liquid, minus the delta H of formation of C3H8 propane. Okay, so I need those numbers. So I can go back to the charts we have, and CO2, that's negative 393.5. We also have a value here for the propane, negative 104. And water, notice that water as a liquid and water as a gas have two different values. So we want to use water as a liquid. So going back, whoops. So 3 times the CO2 number, so 3 times negative 393.5 kilojoules per mole. Okay, plus 4 times the value for the water as a liquid, negative 286, minus the delta H of formation of C3H8, which was negative 104, so minus negative 104. And we're going to put those all together. Okay, so I get negative 1180.5, and 4 times negative 286, negative 1144, and negative 104 is positive 104. And I put that together, I get negative 2,220.5. Okay, and again, that's kilojoules per mole. So pretty good agreement with the number we got on the last problem. Okay, so that's using delta H as a formation, okay, as long as I have all those values. Now, just a quick note, and that is this number and this number, those are actually relatively easy to measure because you can put carbon and oxygen, hydrogen and oxygen and do that. But figuring out the heat of delta H of formation of C3H8, that would be hard to do. You couldn't put carbon and hydrogen and make propane. So you could, however, burn this. So this is measurable, okay, and this one is good, and this one is good. So using this reaction, we could calculate the delta H of formation of C3H8. So this would be findable, this would be findable, this would be findable, and this is what you can calculate. And that's probably where that number came from, the negative 104 that we used off the chart. Okay, the next problem has to do with Hess's law, okay? And the idea here, again, is physically very hard to go from diamond to graphite, okay? But we can theoretically do this because, again, it is relatively easy to burn some carbon, okay, in the form of graphite and turn it into CO2. And if you do, you can measure that it gives off negative 393.5 kilojoules per mole. And you can do the same thing with diamonds, okay, and burn them, and you get negative 395.4. So Hess's law, we want to put these two equations together to get this overall equation, and then we can add the delta H's. So looking at this, I've got carbon diamond on the correct place, so I'm going to use the second reaction just as is. But my first reaction, I'm going to have to reverse this. So I'm going to say CO2 gas turns into carbon as graphite, okay, plus O2 as a gas. And if I do that, then I have to change my delta H. So my new delta H will be a positive 393.5 kilojoules per mole. So what happens here is I take these two equations, okay, I'm going to put them together. My oxygens cancel out, my CO2s cancel out, and I'm left with carbon as a diamond turns into carbon as graphite. And all I have to do now is a negative 395.4 plus positive 393.5. So the delta H for this reaction equals negative 1.9 kilojoules per mole of chemical that changes. Okay, so again, Hess's law lets us put together some relatively easy to measure energies so that we can figure out the energy of something that is not so easy to measure. And that's the quick check.